Welcome to Academic Digest class. Question here says electrons flow from, the answer is higher potential regions to lower potential regions. So we'll move to electric potential and electric fields in three dimensions. The first question we are going to solve this. The question says if the potential field V varies in space, XYZ as follows. V means potential field, or you say yes. So I want to use potential, can be the same thing as potential. I don't want to say potential difference. So but you know that electric potential, so it means electric potential. So this is what we are given, 2x squared y z cube plus 3xy cube is z squared. So then they say obtain an expression for electric field strength in space. I've told you to always consider this electric field strength as electric field, or you say it tells you how strong or weak or the direction of charge, and you know that it's charge that makes for electric field. And you need to know that from this thing that we read up here, that electrons or charge, anything about electric field moves from higher potential region to lower potential region. That means if it is in big quantity, it is decreasing, it is having steepness, so it moves to the part that is steep. Or you say if it is that way, it moves from positive, because you know that if something is adding, it's positive, if something is decreasing, it's negative. That means that electric field is equals to negative potential, or you say negative direction of the change in potential, electric potential. So if it's maybe plus 3 now, it will have to move to maybe -1 or -2. So, or like it's subtracting, so it's moving from higher to lower, and you know that lower means subtracting. So you need to know that, and that is the reason why we have, okay, let's solve this before reading the other questions. So that is the reason, or the answer to this, where it says y is change in V over change in R equals to electric field. So we remember that there is a relationship between electric potential, which is that V is equals to ER. So if you make E subject of the formula, E becomes V over R. So the right answer, or the right way to do this, is simply that E is equals to negative change in V all over change in R. It's the same thing with this. Most times we don't put it, we just write it this way, but it's the same thing here. So if you see, for example, where they now say that this is electric field in the x-axis, it will be the same thing as saying change in potential, electric potential all over change in the x-axis. If it's in the y-axis, you will now have it to be negative change in the electric potential all over change in the y-axis, that is in the distance. Y-axis occupies some length. So if I know that, if I now have electric field in the z-axis, it will be negative change in potential, electric potential all over, with respect, all over means with respect to change in z-axis. So you need to note this, and I said that the reason for this is simply that the reason is that electric or electrons or charge flow from region of higher potential, of higher electric potential and you see potential energy to region of lower electric potential. So you need to know this, which means that you know that electric potential, therefore you know that electric potential, which is given by V, but this thing that we normally say is V is actually voltage. The right way to say electric potential, okay, let me use V though, but the right way, okay, let's go. So electric potential V is equals to work done in moving a unit positive charge from one point to the other. So that is work done over Q. If I know this thing that I have is actually saying, okay, this is the formula from the definition. But when you really want to go deep into calculating this, you need to know, or when you are dealing with fields in space. So when dealing with fields in space, it's important to now consider what this thing actually is. It's no longer when we are dealing with two dimension, how it really works. So what it simply means is that since we know that potential, electric potential is always tending to the negative part, what it means is that this is the same thing as having this to be this way. This means negative V is equals to work done all over Q, because that is what we have. Which means that if I want to make work subject of the formula here, work should simply be the same thing as saying negative V times Q. So this is what it should be like. This is what it should be like. So anytime you are considering voltage, or no, I say voltage, sorry. Anytime you are considering electric potential, always see it that it is in such a way that the movement is to, since the movement is from higher region, and you know that higher region is like addition, addition, like if you have something to be like add a 3 to lower region, it will not be going to like -1, -2, -3. So if something is 3, if you minus it 1, is moving to 2, moving to 1 till it reaches equilibrium. Till it's reach or attains, till it reach, till it gets to, or till it reaches equilibrium, then there will be no flow. So for that reason, it is good positive to negative. So therefore, for fields in space, electric potential carries negative sign. So if I know this, it simply means that if I now come back, okay, if I now come back to this thing that I have here, I will now say that this is the reason why everything here is having negative sign, because this is the same thing as saying, minus, that is minus V equals to ER, or you say also, anyhow. So that means that if you now make E subject of the formula, you should be having minus V all over R. So if I know this, let's move to this one. Then I said electric potential energy or electric work. If you remember, we said that electric potential is equals to work done. And this work done can be kinetic energy or potential energy. all over charge. So potential energy or work done is going to be always equal to VQ. And when it is in space, that is, but when in space, everything here is work. So work. So in space or in three dimension, in three dimension minus VQ, or you say minus change in VQ. So you can put it this way. So it's important to note all these things. Note it that you are a student. Note it you are a student. Now if you know this, voltage is simply the difference in electric potential, or you say electric potential difference, or you say change in electric potential difference. That is V2 minus V1. You can have it to be V3 minus V2. So you know this now. Change in electric potential. So with what you now know, with all these things, the informations that I've given you, as a student, you can now open your brain. You now need to open your brain and concentrate. Stop thinking about any other thing. Let's solve the question that we have. So they gave us V to be this. So I'll now have it to be. Let me write it out. The first thing I told you, V is equals to. They gave us in space X, Y, Z. So they now said V equals to 2x squared. Let me write it out. So they say if electric potential field V varies in space, immediately you see this, it simply means that this thing that I have here is minus V. In space, you consider potential to minus. So if they say obtain electric field in space, what it simply means is that I'll remember that electric field in space, I've given it to you. This is the formula. So E for x-axis will simply be minus dV with respect E on the x-axis will simply be minus dV with respect to change in x. So minus dV. Then that means that this is going to be the same thing as saying and you know that is a vector. So I'm going to be differentiating this. I know that when we did the first semester work, we know that x-axis is the same thing as I, y-axis is the same thing as j, z-axis is the same thing as k. So what it means is that anything I do here, I'll put I to it. That is I to show that it's on the x-axis. I'm differentiating with respect to x, that is length of x on the x-axis. Now EY, okay, that means if I'm doing this now, it will now be the same thing as saying E on the x-axis will be equals to differentiate x-axis now. Differentiate with respect to x. So I'll simply say everything here minus. Okay, let me bring it down here because of this. So E on the x-axis will be equals to minus change in V. Let me change V. This is V. Everything V here. Let me change V. So if I'm changing V now, I will have, with respect to x, I will have, it's a vector quantity, 2 times 2, 4, 2 minus 1, 1, anything raised by 1 is that in x. If you like, don't go and watch the videos on calculus. This time be frowning your face. Can't be teaching you calculus here. And because they are together, because it's multiplying, bring y, bring z, don't differentiate it because it's with respect to x you are differentiating. Then plus, come to this side. Come here, hope I off my airplane mode. Okay, let's go back. Come to me. So I'll come here. This is 1 up here. Invisible. N to the power 1 is times 3. 1 minus 1, 0 into raised to power 0 is 1. So here is 1. X will go. Bring back y3 and z square. Now put I to show that you know that this is a vector quantity on the x-axis. Why is it that so? Anytime you see this thing given to you, notice they did not tell you y, x, z or whatever. They just told you that it happens on all the axes. It's not divergence. I have a video on this when we did gradients, divergence and color vectors. So I've differentiated this now. I'll leave it like this. Now let me do for electric field on the y-axis. So electric field on the y-axis will simply be change in electric potential with respect to y-axis, and y is called J. That is, you show that it's on the on the y-axis by writing J. So I'll now have this to be EY equals to, do the same thing, differentiate everything here, that is the V. It will have minus 2x square. Just carry your x square, come down. You don't have business with it. But notice that the y that is here, will come and multiply these two. Yes, we'll come and multiply not just these two, all these things here, the coefficient, that is the up here. So 1 times everything here, remains everything here. Then 1 minus 1, 0. That means there is no y. So bring down z raised to power 3. If you don't know how to do differentiation, you are not following me, I know. But if you can go and study differentiation, you come back, look at what I'm doing, you will be very happy. You say, chai, academic that. So now let's move 3x. Okay, then see that there's 3 on top of this one is y we are differentiating. We are differentiating with what is on the denominator, y. So 3 times 3, 9. Minus 1, 2. So I will now write, I'm having my x down, no problem. So I'm now write y2. Then write z square. So when you are not dealing with a particular thing, you don't touch it. So it's y with respect to y I'm differentiating, so I can touch only y. So let's move electric field on the z axis now. So on the z axis, I have minus change. You see this thing written like this. I normally write my own like D in V, in electric potential with respect to Z. Put K. So on the Z axis, it will now be minus. So we have 2. Okay, there's 3 here. 3 times, we times the coefficient. So 3 times 2 is 6. 6 x square y z square plus, I have 2 here, 2 times 3, 6 again, plus, plus 6 x y cube z, because 2 minus 1 is 1. So I have this. So at this junction, you put K. You've been able to differentiate. And what have you done? You've been able to show that electric field is simply what you have here. Electric field, well, you've been able to show that electric field is simply electric potential over distance, because all these things you see in x, y, and z, they are distances. X has distance, this has distance, this has distance. That is x distance, y distance, length, and this. You see it. So you've been able to show it, but now, why am I cancelling it? Why are you cancelling? Ah, God. X, Y, Z. So the next thing now is to now go back. You'll be able to show the electric field in space. That is the A part. You'll be able to show it in space. That's our answer. So for option A, if we are to write this now, if we are to represent this now, it will now be the same thing as saying E, X, Y, Z. If we are to show it, it will simply be in this form, equals to, that is minus dv Okay, minus everything in respect to x I plus the v dy j plus the v dz k. So if we put everything together now, we can put everything together. I will do it. Let me turn and do it. So that I will now have everything and carry the value of this. Put for this one. Carry the value of this. Put for this one. Carry the value of this. Put for this one. So that I now have electric field in space. That is option A. Answering it now. I will now have it to be the E equals to minus into 4, I'll reduce my 100 to 4x yz3 4x yz3 plus 3y3 z square or I plus, okay, see how I'll do this now. I'm putting minus because the minus is for all of them. Plus, now, plus for this one now. Minus, yeah, plus 2x square z cube plus 9xy square z square. So plus, remember that there's minus. This minus covers for everything because each one has minus in front of it. So plus, and remember that this one will carry j. So everything here, this one will carry j. So plus that of the z, 6x square yz square. 6x square yz square plus 6xy cube z. 6xy cube z all key. Then close it again. So there you have it. That is for A. So this is the answer to A. The electric field. This is it. So this is it in space. So for the X, for the Y, and for the Z. So I, J, K. So showing that is a vector. So for the B part now, B part of the question says calculate such electric field strength or calculate such electric field explicitly at x equals to 1, y equals to -1, and z equals to 2. It's just like when you do functions. So anywhere we see x, we put 1. Anywhere we see y, we put -1. Anywhere we see z, we put 2. So that means I'll go here for B now. It is simply going to be E equals to, remember that we have minus. Let me just start here. We have minus, E is equals to minus, then I have 4, x is 1, y is -1, z is 2, is raised to power 3, plus 3 into y is -1, z is 2, so I plus 2, x is 1, Z is 2. 9, 1, minus 1 square, 2 square, G, plus 6. X is 1 square. Then minus 1, 2 square. Then plus, let me finish it here, plus 6 into 1 cube, say 1. That cube should be for y. This is for y. So y, so nothing here. So minus 1 cube 2. Okay, so at this junction we can now solve so that we have E to be equals to 4 times 1, 4 times minus 1 minus 4, 2 raised to power 3, 8. 8 times 4. Yes, 32. Okay, but notice that there's minus now, so minus 32. Okay, minus raised to power 3 minus 1. Then this is 2 raised to power 2, 4. 4 times minus 1 minus 4. Minus 4 times 3, 12. So minus 4 times 3 minus 12. So minus 12, there's plus here. So minus 2 and 2 will add up 4. 10 and 30, they will add up 44. So I have minus 44 here. Minus 44i. But notice that, remember that there is minus sign inside. Whatever we get, we'll use minus to multiply through everything. Be active, boy. So I now have 2 raised to power 3 is 8. 1 raised to power 2 is 1. 8. Yes. 8 times 2, 16. So I have 16. Plus. Minus raised to power 2 is plus. So 2. So 1. This is positive 1. This is 4. 4 times 1, 4. So 9. 4 times 9 should be 36. Because it will be 18, 36, 36. So by the time you add up 36, 6 and 6 will give you 12. Shebi? Give you 12. You write 2, carry 1. 30 and, yes, 30 and, so 30 and 10 will give you 40. Is it supposed to be 52? Let's go through it this way. This and this. 40. 46. 46. By the time you carry 6 and come to it, it will now give you 4 to it, 50. 46 here, 4 to it, 50. Then to remain 52. So 52. Yes. So whatever you get, you still multiply through with minus. Then let's come over to this place, baby. So I will now have raised to power 2, 1. And there's minus. So 6 times minus 6. Minus 6 times 4. This is 4. 2 raised to power 2 is 4. So 4 times 6 should be 24. 24. But there's minus 24. Minus 24. Then let's come here, baby. So I have minus 1 times 6 is 6 times 2 minus 12. So minus 12 and minus 24. This should give me 6 and 3. So minus 36. Yes, guys, by the time you are adding it up, so you have minus 36 minus We carry 30 to 34. Yeah, minus 36. So collectively minus 36. So what this thing means is that I have minus here. Minus times minus is plus. So I have 44I. Yes. Now I have minus here. I have plus here. I have minus 52J. Then I have minus here. I have minus here. Plus 36K. So the B part is now going to be 44I minus 52J plus 36K. There you have it, babe. So let's move to the second question. Second question says, if a charge Q is equals to 1.9 times 10, remember, before I move on, how much work is required to move a 500 microcoulomb charge across potential difference of minus 250 volts? So that means you already know it. You should remember that I gave you a formula, and that formula is that V is equals to work done over charge, work done in moving a unit positive charge, or you moving a charge from one point to the other. So if this is the work done, that means that, and remember that if we are talking about space, or if we are talking about this proper, what this should be negative. So that means work done is equals to minus VQ. This is the formula to use when you are solving this for me. So you convert microcoulomb to coulomb. 1 million microcoulomb is equals to 1 coulomb. So that means raised to power 10 raised to power minus 6. So you do it, then multiply with. So do this one. Why am I even telling you? Question 3 is your assignment and classwork. So let's solve question 2. Call it a day. The charge Q equals to 1.9 times. God. Okay. Stress. But let's try. So they say calculate the force on the charge. That's what we are doing. So let's see how to go about it. Read the question. This is the question. If a charge Q 1.9 times 10 raised to power minus 3 coulomb is placed at position x equals to 1, y equals to minus 2, z equals to 3, giving us V, that is that potential difference. Anyway, you see it's V equals to 4x cube y z raised to power 5. Calculate the force on the charge. So let me start. So question 2. So question 2 solution. They gave me V. This is the most important thing I'm looking for. And they gave me V to be equals to 4x cubed yz raised to power 5. 4x cubed yz raised to power 5. This is the important thing I'm looking for. So I can now remember that I cannot solve. I can remember they said I should find. Sometimes, if you are not really active in reading, you think these things are difficult. But if you are reading, you now be connecting whichever one they ask you. They're asking me to calculate the force, and this is electricity we are dealing with. Electric force is given by QE, if you remember. Electric field and charge. They gave me charge, but they did not give me electric field. I need to find electric field, and since it's given to me in this way, I need to use the formula, which is for space. So I will need to say that E is equals to negative change in V all over change in R. And since we have X, Y, Z here, it simply means that E on the X will be changing in the V with respect to change in the X, negative. And on the Y axis, it will be negative change in V with respect to Y. And on the Z axis, it will be negative change in V, change in Z with respect to Z. So if I know this, I will now have this now to be the same thing as saying for the x-axis, let me differentiate it. So E on the x-axis will simply be the same thing as saying, I like putting it, no matter how many times I do it, I like putting it because some of you people behave, if you don't put it, you will just forget that I already said it. Some of you are paying attention, but you are eager to be doing another thing. It's alright. It's you that know your reason for doing academics. If you can't do it attentively, why don't you start business, open shop, start selling pen and book? So now, if I differentiate this, I will now have 3 times this, it will be 12x, 3 minus 1, 2, y, z, 5. You are like, how did he do this? Go and watch calculus video. I've differentiated this, but I'll be doing this the same time so that I don't waste my time. They said that x is 1 in the question. They said that at position x equals to 1. So since x is 1, remember that everything here is always carrying negative sign. Then negative 12 x is 1 square. Y on the question, y is minus 2. Y is minus 2. Z is 3. Minus 2. Y raised to the power 2 is 1. So times this is 12. So 3 raised to the power 5. I know that 3 raised to the power, if you do 3 times 3, 9 times 3, 18. I beg. 3 raised to the power 5, 243. No get strength. So I'll now have times minus 2 times 243. So you now see that this is going to be minus 2 times 12 times 243. So I have equals to minus 5,832 minus, which means here it will be plus 5,832. So I remember that everything we are doing here is supposed to be having I. That is what shows that is a vector. I. So I. Now on the y-axis, it will be the same thing as saying minus change in v with respect to y, then g is equals to, so I now have 4. Remember that this is 4. Okay, y is not carrying anything, so 1 times 4 is 4x cubed. 1 minus 1 is 0, so y is gone, so z 5. So, and it's on the j part. Remember, it will carry negative sign. If you don't do it, sometimes you think it's only for one value. Always do it this way so you don't confuse yourself. So I'll now have this inside minus 4 into y is 1, x is 1, that's power 3, and z is 3, raised to power 5. So this will be the same thing as saying, so 4 times 243. 4 times 243 equals to 972G, and it's having negative sign. So negative 972G. So on the z-axis, EZ is equals to negative changing electric potential with respect to Z equals to minus So I have 5 times 4 is 20. 20x cube ring y. 5, see where I am. This is the one I differentiate. I did 5 times 4. This is the one this is the main thing. The change in v simply means differentiate. So 5 times 20. So now minus 1 from 5 is 4. So I have z raised to power 4. Big things. So I now have equals to, is going to be minus 20 into 1 raised to power 3. Then y is minus 2. Then z is 3 raised to power 4. And remember it's on the key. So this is going to be 3 raised to power 4. 3 raised to power 4 is 81. 81 times minus 2, then times 20. Or minus, okay. So let's do it. 20 times 2 times 81. So this is going to be minus 3,240k. And notice that there's minus outside. This minus made this one. So it will be plus. So equals to 3,240k. So on the E on the Z axis. So this is what you have. So now, remember that the question, the actual question said that what we should do. Let's go back to that question. The question says calculate the force on the charge. So that's why we had to find E, because we already have charge. The charge is 1.9 times 10 raised to the power minus 3. So to find force, so we do since Q equals to 1.9 times 10 raised to the power minus 3 coulomb. Yes, coulomb. And I've gotten E. And E equals to 5832I. 5832I minus 972J plus 3240K. Therefore, force being equals to QE, assuming they gave me mass and acceleration, it will be MA equals to K, but since there's nothing like that, so electric force will be equals to Q. Q is simply 1.9 times 10 raised to the power minus 3. So it will times my E, and my E is simply 5832I minus 972J plus 3240K. So let's do that. So if we do that, you now see that you can never add this when the signs are not the same. Remember, it's first semester work. So I now have 1.9 times 10 raised to the power minus 3. So we have 1, 2, 3. So we have this to be the same thing as saying, okay, yes, times 5832. So we have F is equals to 11.08I minus 1.9 times 10 raised to the power minus 3 times 972. So you have 1.8468 or 1.85. So plus 1.9 times 10 raised to power minus 3 times 3242 equals to 6.16. 6.16. Remember that this one will carry its J, and then this one will carry its K. So there you have it. This is our force. This is our force. And you know that force is in Newton. So this is our answer. Thank you. Subscribe.